Welcome to the Mathematical Constant Iceberg. This is my first ever iceberg video, and I used AI voice to narrate it. Sorry for my bad English. Please enjoy. So mathematical constant is something that will be the exact same, and if we change a tiny bit of it, our universe could collapse. So let's start this fast iceberg. Layer 1. This tier, the entries are very common, so I will just go over them fast. 1. 1 is considered to be the first positive number. 1 is 1, nothing else. In philosophy and science, 1 can symbolize the idea of singularity or uniqueness. It's one of two digits in the binary system, along with 0, which is the basis of all modern computing. 13. 13 is just a prime number. But in Western superstition, 13 is often considered unlucky, leading to triskaidekaphobia, fear of the number 13. This belief has roots in Norse mythology and Christianity. Cus Judas was the 13th guest at the Last Supper. But I think it's just a misunderstanding because it often appears in stories and movies, adding a sense of mystery or danger. 420. 420 has become a symbol in memes and jokes, often associated with rebellious or laid-back attitudes. The number 420 is widely associated with marijuana. It originated from a group of Californian high schoolers in the 1970s who used 420 as a code to meet at 4:20 p.m. to search for cannabis. 69. 3 times 23 is 69. It just looks the same when rotated 180 degrees. But the number is used in pop culture as a reference to a sexual position due to its appearance, which has made it a staple of memes and jokes. It's often used in jokes or as a punchline because of its visual symmetry and associations. 2 is like 1 but opposite. Duality is a fundamental concept. In essence, the number 2 is a cornerstone of mathematics, science, and culture, representing balance, duality, and foundational structure. It's something that is not 1. 999, repeating nines. It's just always 1, less than a new decimal or numerical group. Once again, 1 less, 7. 7 is another misunderstood prime number like 13. In many religions, 7 is considered sacred. In Islam, there are 7 heavens mentioned in the Quran. In Christianity, God created the world in 6 days and rested on the 7th. In Hinduism, 7 chakras are central to spiritual practice. In many cultures, 7 is viewed as a lucky number, symbolizing good fortune and perfection. 1 plus 2 is 3. Once again, it's just another extremely common number. We live in a 3D world. Clovers, trilobites, and animal tracks often form patterns of 3. 3 could be seen in many religions as an important number. Trinity is just another useful, cool number. 0 is a number. It's the only number that was proven to be a number by Indian mathematician Brahmagupta. 0 means nothing, no thing. It is an extremely useful number that is special as it is the most unique number. It is something that everything was and will be. In many philosophies, 0 represents nothingness or the void, and is often seen as the origin or a state of potential. In the binary number system, 0 and 1 are the fundamental digits forming the basis of all digital technology. Layer 2. This layer is almost like the previous layer, so I'll just go over it fast. -1, the complete opposite of 1, but at the same time, it's 1 but negative. In the world of complex numbers, 9 of 1 plays a key role, especially when paired with the imaginary unit. The idea of opposites or duality plays a key role, like there's always a good guy and bad guy, positive and negative, dark and light, and so on. -2. Let's not waste time with these. -99. Same thing but negative. -1, 2, 3. The number Nash 123 is just another negative number. 1 divided by 4. The fraction 1/4 is a simple but powerful mathematical concept, commonly encountered in various disciplines, from basic arithmetic to more advanced fields. From slicing a pizza to being quarters, it is 25% of a thing. The sum of 5 is fun, but 25 has something special. 1 divided by 2. Same as our previous entry, it's half, 0.5, or 50%. Once again, if something is 1, we people like to make it 2. It is one of the most common divisions of a whole. It symbolizes balance and equality since the whole is equally divided into 2 parts. In cultural contexts, dividing things into two parts is often seen as creating a balance between two opposites or complementary forces, one divided by 69. Why are people so obsessed with 69, man? 1 divided by 3. For me, it's one of the most interesting ratios because just like pi, it never ends. It's just 0.3333333333333333, and it will keep going. And the fun fact is that if we divide 100 by 3, we will never get equal parts. Unlike 1 by 4 or 1 by 2, it never matches. Something about 3 is indeed very odd. Layer 3. This is where all the fun part begins. Buckle up. Divided by infinity. The closer you get to dividing 1 by a larger and larger number, the smaller the result becomes. If you keep increasing the denominator, the fraction approaches 0. As the denominator grows infinitely, the result keeps getting closer to 0. It's not that dividing by infinity equals 0 directly, but rather that it approaches 0 as the denominator becomes larger. So it's an asymptotic relationship. Infinity isn't a fixed number, so the result of this division is a tendency towards 0, not an exact number. Pi. 3.1415965599784466438327952841971169 and so on. It never ends. Pi is an irrational number, meaning it cannot be expressed exactly as a fraction of two integers. Its decimal expansion goes on forever without repeating. Pi is fundamentally tied to circles. It is the ratio of the circumference of any circle to its diameter. In other words, for any circle, pi is the ratio between the circumference and the diameter. Pi is a remarkable number that continues to fascinate both mathematicians and those who see it as a symbol of deeper philosophical and cosmic truths. It probably meant the imaginary number, but that's for another video, as it is about just constant numbers. The square root of -1 could be considered a constant, but I think we all know what it means. The Starschat Euler's number minus e is the base of the natural logarithm. The natural logarithm is the logarithm to the base e. The exponential function e to the power of x is one of the most important functions in mathematics, appearing in a variety of contexts such as growth, decay, and calculus. It is by far the most interesting entry on this list, and E is approximately 2.71828. From birth rates to tree growth to animal decay, it is everywhere. It reflects how change happens continuously, and this has made it important in not only mathematics, but also physics, economics, and biology. Philosophically, this resonates with ideas of impermanence and evolution. Just as the number e represents continuous and exponential change, some philosophers argue that change is a fundamental aspect of existence itself. We are living in a simulated world made by God, and everything is predetermined. I could make an entire video on this. 3 Blue 1 Brown has a great video on it. You can check it out. 10 to the power of 100. 10 to the power of 100 is the term Google, coined by Milton Serrata, the nephew of American mathematician Edward Kasner, in 1938. A googol is a number that provides a philosophical exploration of vastness and human limits, often used to contrast the finite nature of numbers with the conceptual idea of infinity. It is very simple. Square root of 2. The square root of 2 is by far the most popular irrational number, like pi. It is the first rooted number as well. Root 2 is not just a number but also a symbol of mathematical depth, challenging the very idea of rationality and perfection in numbers. It opens up deeper philosophical questions about the nature of reality, the limits of human understanding, and the infinite, reflecting a timeless tension between order and chaos in both mathematics and life. Layer 4. This layer, we got some entries that you might have never heard of. Rayo 10 to the power of 100. Okay, this one was hard, but I tried my best to describe it. So, Rayo's number was created during a discussion about the largest describable finite number as part of a contest in big number theory. It was proposed by Agustin Rayo, a philosopher, during a 2007 competition. Basically, Rayo's number works by using a rule. It's the smallest number bigger than any number you can describe with less than a googol, 10 to the 100 symbols. These symbols include numbers, math operations and logical notations. For example, you can describe a googol or even huge numbers like Graham's number with far fewer symbols than a googol. Ryo's number takes all possible numbers you could describe this way, no matter how big, and then defines itself as bigger than all of them. Okay, stay with me and imagine you're in a contest to build the tallest tower using fewer than a Google Lego blocks. People build all kinds of towers, some as tall as mountains, others as tall as the sky. Just when you think you've seen the tallest one, Ryo's tower appears. It's not just taller than any tower built so far, it's taller than any tower that could ever be built with those blocks. It doesn't just beat the competition, it outpaces the very idea of what's possible within the rules. It's like saying, no matter what giant number you can describe, I'm even bigger. Phi, the golden ratio by Euclid. It is approximately 1.61803987 and is an irrational number. It's special because it appears naturally in art, architecture, nature, and mathematics. Like spiral patterns in sunflowers, pine cones, and shells follow the golden ratio. The Parthenon, Da Vinci's Vitruvian Man, and many Renaissance artworks use it for balance and beauty. It's closely related to the Fibonacci sequence, where the ratio of successive numbers approaches phi. Phi is seen as a symbol of harmony and balance, representing beauty and order in the universe. Many believe it connects mathematics and aesthetics, bridging the logical and the emotional. But one question: why is this ratio so beautiful? Why does our mind like it so much? I guess we'll never know in this life. It's kind of like Euler's number. There's so much more to it, and you should definitely check out other videos on it. Aleph null. The concept of Aleph null was introduced by George Cantor in the late 19th century. Before Cantor, infinity was often tied to religious or philosophical ideas of the infinite being, like God or the universe. With Cantor, infinity became a measurable concept, something mathematics could work with and understand logically. Aleph null is the mathematical symbol for the smallest infinity. It represents the size or cardinality of any set that can be put into a one-to-one correspondence with the natural numbers. This is called countable infinity. The set of natural numbers like 1 plus 2 plus 3 plus 5 plus 6, etc., has this cardinality. Even though some of these sets look smaller or larger, Cantor proved they are all equal in size. They all share the same cardinality. Aleph null challenges our intuition about size, order, and the nature of infinity itself, bridging the gap between mathematics and the abstract mysteries of existence. Omega. By George Cantor again, the symbol represents the first infinite ordinal number, also known as omega. It describes the order type of the natural numbers extending endlessly. The concept of omega, often paired with notations like OO or OMW, comes from ordinal numbers in set theory, introduced by George Cantor. While cardinal numbers measure the size of infinite sets, ordinal numbers describe the order or position of elements within those sets. Omega is the next step after all natural numbers. Imagine counting endlessly through all natural numbers 1, 2, 3, and then saying, what comes next? The answer is omega, omo. It represents the smallest infinite ordinal, marking the first infinity in the context of ordering. Omega reminds us that infinity is not static. It can be organized, ordered, and extended further, showing the dynamic nature of infinity. Tree 3. The number tree 3 comes from a branch of mathematics called combinatorial game theory and was introduced through graph theory. It was first defined in relation to a specific mathematical challenge called the tree sequence problem, which involves exploring all possible finite trees, connected structures with no cycles under strict rules. It is related to the study of extremely large finite numbers that arise in Ramsey theory. Tree 3 is an unimaginably large finite number that emerges when you attempt to explore all possible ways of constructing finite trees under a specific rule system. Here's me explaining it to you, but I know I'm very bad at it. Start with a tree, a structure of connected nodes with no cycles. Add nodes or branches according to coloring rules, a combinatorial condition. Continue the process until no new trees can be added without breaking the rules. The tree sequence grows explosively as you add more nodes and constraints, and Tree 3 is the point where you cannot add more valid trees under the rules. Tree 3 represents the mind-boggling complexity of finite systems. It challenges our understanding of large numbers and reminds us of the limits of human intuition. I highly suggest you watch some videos on this game as it's extremely fun. You can even play it yourself. It's kind of a time killer for people like me. Lol. Tau. The concept of tau arises as an alternative to pi in mathematics. Pi, approximately 3.14159, represents the ratio of a circle's circumference to its diameter. However, mathematician Michael Hartle and others propose that using the circle's radius instead of the diameter leads to a more natural constant, tau, which equals 2 pi, approximately 6.28318. Hartle argued that tau simplifies formulas and improves understanding in geometry, trigonometry, and calculus. In simple terms, it's just an alternative to pi, and tau is equal to pi times 2. Layer 5, ta, ln2, the natural logarithm of 2, denoted as ln2, arises from the concept of natural logarithms, logarithms with a base of Euler's number e, 2.71828. Natural logarithms are widely used in mathematics, physics, and engineering to describe growth, decay, and scaling. ln2 specifically measures the time, growth, or steps needed to double something under continuous exponential growth. The formula for doubling time is ln2 divided by r star, where star r is the growth rate. It answers the question, how long does it take for something to double under continuous exponential growth? In contexts like population growth, finance, and radioactive decay, ln2 helps calculate the time it takes for something to double. It symbolizes the concept of doubling, a fundamental idea in nature and life. It represents growth, change, and transformation over time. It's one of those things that can sometimes calculate the future, giving an uncanny feeling, almost as if we live in a simulation. Gamma. Something like ln2, the Euler-Mascheroni constant, commonly denoted as gamma, was first introduced by the Swiss mathematician Leonhard Euler in the 18th century. It arises in the study of the harmonic series and the difference between the natural logarithm and its partial sums. Euler noticed that as you sum the harmonic series and subtract the natural logarithm of the same terms, the values approach a constant, which is now called gamma. Gamma represents the gap between two mathematical worlds: discrete steps, harmonic series, and smooth, continuous growth, natural logarithm. It appears in prime number distributions and in relationships involving factorials, thermodynamics, quantum field theory, and signal processing, particularly when analyzing certain limits or growth rates. Despite its frequent appearance, gamma has no simple closed-form expression, highlighting the mysteries and limitations of mathematics in describing nature. Apéri's constant. Apéri's constant, denoted as Z3, zeta of 3, is named after the French mathematician Roger Apéry, who proved in 1978 that this number is irrational, a groundbreaking discovery at the time. Apéry's constant comes from the Riemann zeta function, a key function in number theory. Its approximate value is 1.20205699. It appears in problems related to prime numbers, and sums of powers of integers. Beyond pure mathematics, it arises in quantum physics, particularly in studies of electron energy levels and thermodynamics. It also shows up in calculations involving signal processing and statistical mechanics. Apéry's constant symbolizes the beauty of order within chaos. While it arises from a simple series of cubed reciprocals, its irrationality reflects that even seemingly neat mathematical structures hide deep, unending complexity. I'm too lazy to explain all of it, so just go ahead and watch other videos on Apéry's constant if you're interested. It's damn fun to know. Rho. There isn't a single universally recognized rho constant like pi or e, but rho can represent constants or parameters in specific fields of mathematics, physics, and science. In physics, rho often denotes constant density, such as mass per unit volume. In statistics, rho represents the population correlation coefficient, a measure of the strength and direction of a linear relationship between two variables. In electrical engineering, Joule can denote electrical resistivity, a constant that describes how strongly a material opposes the flow of electric current. In geometry, curvature might represent specific radii, such as the radius of curvature or distances between certain points in space. Rho is a versatile symbol used across disciplines to express key ideas, connecting abstract mathematics to practical science and engineering. Layer 6, J. I'm extremely sorry as I don't even understand what it means. Probably not joule. It could be the imaginary number, but we've already covered that. It might be a symbol that looks like J, but I've gone through Latin, Greek, Cyrillic, Hebrew, and script alphabets, and I don't think I saw anything like this J that is a mathematical constant. If you know, please tell me in the comments. K is for constant. Yes, I'm serious. In German, it corresponds to Konstante with a K. So basically, most of the constants in math and physics that don't have their own symbol use K to represent themselves. Gaussian curvature, thermal conductivity, wave vector, reaction rate, temperature, Hooke's law, chemical reactions, etc., often use K to represent themselves. It's not mind-blowing, but it's still very cool to see K becoming the symbol for constant instead of C, epsilon. The symbol epsilon comes from the Greek alphabet and is often used in physics and engineering to represent various parameters. The subscript 0 indicates that this is a property of the vacuum, empty space. The concept was formalized during the development of Maxwell's equations in electromagnetism in the 19th century. The permittivity of free space, is 0, is a fundamental physical constant that describes how an electric field behaves in a vacuum. Specifically, it measures the ability of free space to permit electric field lines to pass through it. S0 is a key parameter in Maxwell's equations, which describe electromagnetism and predict the existence of electromagnetic waves like light. The vacuum permittivity, N0, represents the invisible properties of space itself. It highlights that even empty space has measurable physical characteristics. It isn't truly void. This constant connects the microscopic world of electric charges with the macroscopic behavior of fields, suggesting a deeper unity in nature. So even if there is nothing, there is something to measure. Even if you think void is just empty, wait till you learn the amount of things needed to run that place. Zeta subscript 0. Once again, I'm sorry as I don't fully understand it, but I do know zeta, so here are some details. The Greek letter zeta is often used in mathematics and physics, particularly in areas like number theory, fluid dynamics, and electromagnetism. The subscript 00 typically indicates a base reference value, such as in free space, initial conditions, or vacuum states. Sometimes referred to as this, not Z0, but visually similar, it represents the characteristic impedance of free space. This value describes how electromagnetic waves propagate in a vacuum. And that's it. I don't have enough knowledge of it. Layer 7, light stand. Mills constant. Mills constant arises from the work of William H. Mills, an American mathematician who discovered this constant in 1947. Mills was exploring prime generating functions, formulas that generate prime numbers. His work was published as part of a study on sequences of primes. Mills's constant, denoted as m, is an irrational number approximately equal to 1.3063378863006904661444926. Mills's constant is defined through a special property involving prime numbers and powers. If you raise Mill's constant to successive powers of 3 and then round down using the floor function, the result will always be a prime number. Mill's constant symbolizes the mysterious and hidden connections in mathematics. Prime numbers, which appear seemingly random, can emerge predictably from a single irrational number raised to structured powers. This challenges our intuition about order and chaos, demonstrating how even in something as seemingly unpredictable as primes, there are hidden patterns waiting to be discovered. Champernowne constant. The Champernowne constant is named after the British mathematician David Gawain Champernowne, who first introduced it in 1933. Champernowne was exploring normal numbers, numbers in which every possible sequence of digits appears equally often in a given base. The Champernowne constant is a normal number formed by concatenating all positive integers in sequence. For example, in base 10, 0.123456789112131314115. Here, 1, 2, 3, 4 are written consecutively, forming an infinite decimal expansion. Champernowne constants can also be defined in other bases, e.g., binary base 8, where digits of all integers are similarly concatenated. The Champernowne constant beautifully connects order and randomness. At first glance, its construction seems trivial, just concatenating all integers. Yet this seemingly simple sequence encodes a profound equal distribution of digits in an infinite space. I highly recommend checking this one out, as it's one of my favorite constants. Sadly, I'm too lazy to explain further. Layer 8, the final layer, Yi-base. The Yi-base constant is an obscure mathematical concept emerging from the niche field of googology, a playful and theoretical study of extremely large numbers, constants, and numerical curiosities. The constant was coined and introduced by Garrett Wilkinson, a contributor to googology discussions, and exists primarily on platforms like the Googology Wiki. Unlike constants such as pi or e, the Yibas constant doesn't originate from mainstream mathematics or physics, but rather from a creative exploration of numbers. The Yibase constant is approximately 5.9234434566455888458544745. While its exact definition or derivation remains unclear in traditional mathematics, it represents a constructed constant for the sake of exploring the boundaries of numerical imagination. It lacks rigorous proof, equations, or real-world derivations like classical constants, but exists as a theoretical or recreational construct. The Yi-base constant does not have conventional uses in mathematics, physics, or engineering, like pi, Euler's number, E, or the speed of light constant. Instead, it reflects the creativity of the googology community, which often invents constants and vast numbers as a way to challenge our understanding of magnitude, complexity, and the limits of symbolic representation. Some say the Yibas constant could be hiding a deeper, unknown mathematical relationship or pattern waiting to be discovered. Its seemingly random nature, paired with its oddly specific value, 5.9234, gives it an allure. Why does it exist? What does it mean? If you're intrigued by mathematical mysteries that defy mainstream attention, like Easter eggs in the world of numbers, the Yibas constant is a rabbit hole worth diving into. Could it be the key to an undiscovered framework of thought? Or is it simply a whimsical creation? Only those who look deeper can decide. Longyai bucket. The term Longyai bucket was coined by Garrett Wilkinson, a contributor to the googology community, a field dedicated to the study and creation of large numbers and numerical concepts. The Longyai bucket can be seen as a playful metaphor. Imagine a bucket so large it can contain not just massive numbers, but entire systems of thought, processes, or constructs that explore large in ways beyond comprehension. In googology, it is likely placed as a step above conventional naming systems, inviting comparisons to entities like Graham's number or other incomprehensibly large finite numbers. While it doesn't hold a defined formula, its name itself implies scale and expansiveness, something so vast it could bucket an infinite number of possibilities. The Longyai bucket is defined as a small fractional value, 7.67 times 10 many score. In mainstream mathematics and science, the Longyai bucket does not have a recognized application. Within the googology community, it serves as an example of creative numerical nomenclature, illustrating the exploration of both extremely large and extremely small numbers. Such terms are often used for educational purposes, thought experiments, or as part of a broader effort to understand the limits of numerical representation. Short Yai bucket. The term short Yai bucket originates within the googology community, a playful yet intellectual niche dedicated to the exploration of incredibly large and small numbers. Like the long Yai bucket, the short Yai bucket was coined by Garrett Wilkinson as part of an effort to conceptualize small yet distinct numerical values. The short Yai bucket is defined as an even smaller fractional value compared to its counterpart, the long Yai bucket. The short Yai bucket would represent a smaller scaled variation, potentially closer to 10 Manchurt or smaller, though its exact value isn't widely standardized. The short Yai bucket has no formal application in mainstream mathematics, physics, or science. However, it serves an essential role in googology, the branch of study where numbers are created, explored, and celebrated for their novelty. It encourages thinking about orders of magnitude so small they push the boundaries of imagination. In theoretical frameworks, it could be compared metaphorically to quantum scales, where incomprehensibly small measurements are necessary to describe physical phenomena. This layer 8 was pretty hard to find out as I had to go through multiple Wikipedia and Googology webs. I highly recommend you finding out this stuff by yourself. It would be more fun that way. And that's it. That was my first iceberg. And while writing the script, I loved it, and I'm definitely going to do more of it. I usually get 5 to 10 views, but I'm putting my effort into these videos because I like it and it might go viral, which has a 10 t mean z% chance. Anyways, pardon me for my bad English and some other mistakes that I probably made, but I really appreciate your time and I'm really, really thankful. And as always, thanks for watching.